Hi everyone, thanks very much for inviting me to give a talk here. So just briefly to acknowledge a couple of people who helped me about this. So this is what I'm going to present today is in large part the section of the white paper that is this section 222, and here are the contributors of this section. So what I'd like to tell you about is how we can try to use galaxy clusters and the abundance of galaxy clusters as tools to understand cosmology. And here to illustrate this point, I'm showing you a simulation of the large-scale structure, which is taken from the Illustris TNG. I think this is TNG 100. And what I'd like you to think about is look at this evolution of these nodes here, where you see that with time, so here at the top you have the gas density, this is the dark matter density, stellar density, and you see that with time these nodes here get bigger and bigger under the influence of the growth of the large-scale structure. And at the nodes are located galaxy clusters, which are the most massive structures we have today in the universe. And another panel that you can focus on is this one here. And this is the gas temperature. So when clusters, well, generally speaking, when structures form, then the potential well gets stronger and stronger. And when that happens, the gas that is embedded within this large-scale structure gets heated up to higher and higher temperatures, and until you get to these red regions here, which are the central regions of clusters where the gas reaches temperatures of 10 to the 7 to 10 to the 8 Kelvin. So it means that in those massive clusters, there is a lot of gas. Actually, the majority of the baryonic content of these structures is made of gas, and with very, very high temperatures. So how can we use these clusters as a way of understanding cosmology? This is highlighted by this plot here. We are using the so-called halo mass function. So the halo mass function is just the number density of dark matter halos per unit volume and per unit mass. And what you see here, this is an old plot back from the Millennium simulation, where you have the evolution of this halo mass function with redshift, where at high redshifts here, this is the curve for redshift 10. At high redshifts, you had this very steep halo mass function where the massive halos had not formed yet. And then under the influence of gravity, these structures are getting bigger and bigger. And when they do, then you're forming ever more massive systems until you see here this at redshift 0, the most massive clusters that we have, they have a mass on the order of 10 to the 15 solar masses. So the evolution here and the overall, in fact, just the low redshift shape of this mass function, they are strongly dependent on cosmological parameters. So we can see that through this little animation here. So here what I'm showing is the mass function at redshift 0 and as a function of omega matter. So here I'm changing here, this is for omega matter 0.1, and you see what happens when I let omega matter change. Then simply we have more and more mass in the universe, so when that happens, we just generate more and more halos. Similarly, it's not just the low redshift halo mass function that contains cosmological information, it's also its evolution with redshift. So here what you have, this is the just the cumulative number of halos above some threshold, which I set as 10 to the 14 solar masses, as a function of redshift. And this is for the case with no dark energy at all. And then this is what happens when you include dark energy. Then when you do that, you get a stronger and stronger evolution of the number of clusters with redshift. So it means that by constraining this halo mass function and its redshift evolution, we can get both to understanding the overall amount of matter that we have today and also understanding sigma 8, because the more clumpy the universe, the more clusters we generate. And then if we are also able to use to determine the evolution of this halo mass function, then we can constrained dark energy as well. So how does it work in as a primer? Let's say you are able to detect clusters. And here I'm showing you, of course, an image that we would love to have for every cluster in the universe, but that we will never get, which is the image of one of the frontier fields clusters. This was a very, very deep observation with HST. But let's say you have a cluster survey where you can detect lots of clusters. Then out of that, you will measure a quantity, that we call an observable. And you want this observable quantity to be related to the mass, because the mass is generally not directly a measurable quantity. But then if you know how this observable quantity of yours is related to the mass, then you can get back to the mass distribution of the systems that you've detected. On top of that, of course, you need a selection function. So you need to know how well you're able to detect your systems given this observable that you're using to detect them. And then when you put those things together, then you can reconstruct your halo mass function and you can fit your cosmological model. So that's, say, the general idea of how this works. There are, of course, out of that, a number of ways of detecting clusters, and the key, of course, one of the key steps here is to have a survey that allows you to detect a lot of them. So there are two main ways of detecting clusters. The first one is through the gas. As I told you, in these massive structures, there is a lot of hot gas. And if you detect hot gas, then this is a direct probe that there is a massive halo underlying here. And this is showing you here by this X-ray emission from this coma cluster here. And the emission that you detect, it goes like the square integrated electron density. The other way that you have to do this is the Sunyaev-Zeldovich effect, which I will call SZ for the remainder of this talk in order to avoid having to say the name of these people over and over. And that is the inverse Compton scattering of CMB photons of the hot electrons of the cluster. So when the CMB photons go through the cluster, sometimes they make a Compton scattering, and when they do that, then you can alter the spectrum of the CMB, and out of that you can detect clusters. So how does it work in X-rays? We have X-ray surveys. The most recent one is Rosita. And if you look at an extragalactic patch of sky in the X-ray and you detect an extended source there, chances are it's a cluster, meaning chances are very, very high that it's a cluster. So essentially any extended X-ray source that you will detect in your survey will be a galaxy cluster. So here I'm just showing an image of the so-called IFET survey, which is this first survey that was done by Rosita at the beginning of the mission for 120 square degree. And if you zoom on some patch of the survey, this is what you see. So you have essentially two types of sources. You have point sources, which are AGN, and you have extended sources, which are clusters. And your primary observable in this case is the luminosity of these systems in the X-rays, which we think is a proxy of the mass of the halo. Then another way of doing that, as I said, is the SZ signal. So that's here I'm showing the case of the SPT SZ survey, which is this 2,500 square degrees. And on the right-hand side, you have a zoom in on one of the patches of the SPT area, and you see, first of all, you see these white dots here, which are millimeter point-like sources. And then you see these shadows here, these sort of black dots, and these are the clusters. Okay, my dots are not at the right place, sorry, I don't know why. But anyway, maybe here you can see them better. Here is a black dot, which is the fact that we are missing flux because it's been upscattered to higher frequencies. And your primary observable in a case like that is what we call a Compton parameter, YSZ, which is a sort of the integrated energy, thermal energy content of the system. Then, of course, we have another way of doing this, which is sort of the classical way, and that is to just count galaxies. And if you find a region of your sky where you see lots of galaxies, then there are chances that there's going to be a cluster there. The main advantage of this is that it has high sensitivity, but there is a strong impact of projection effects if you only have photometric data. So there's a chance that clusters are just gonna, what you think is a cluster is actually going to be a collection of unrelated galaxies. So there's a number of ways of doing that. I'm not going to do into the details here, but let's say we have, in the case of Euclid, there was the Euclid photometric cluster detection challenge that was put together a few years ago, where a number of groups were asked to apply their detection algorithm on a set of mock data. And what you see here is the purity versus completeness. So purity meaning the fraction of your sources, of your detected sources, which are real clusters. Completeness being the fraction of the fraction of the clusters that you're actually detecting. And so in this case, the primary observable is the so-called galaxy richness that we call usually lambda. And that's essentially just the number of galaxies per square degrees in this patch of sky. Then the newcomer in town is direct shear detection. So nowadays, with the latest surveys, we are able to construct weak lensing maps, and then out of that, you can try to find peaks in these weak lensing maps with the match filter technique and directly identify clusters through their lensing signal. And this is, of course, very promising because it's a detection from the dark matter rather than from any baryonic component. But so far, we only have a few of these systems detected, like less than 100 of them. But this should kick off in the future, especially with Euclid. The primary observable here will be the signal to noise of your shear detection. Then what you want to do is to construct a so-called scaling relation. And so by scaling relation, we mean a relation between the survey observable that you used to detect your systems and the underlying mass. And what you want, ideally, is you want this scaling relation to be at the same time low scatter and cheap. Low scatter in the sense that the quantity that you're measuring is well related to the underlying mass, and cheap in the sense that it's easy to measure. So here you have an example, which is the relation between the mass and the temperature. And here this is a case of a low scatter proxy. So you see that the temperature is very closely related to the mass of the system, but it's also expensive because it requires good quality data in order to measure. On the other hand, you have the galaxy richness, which is the primary observable for optical cluster samples. And that is, on the other hand, very easy to measure because you just count galaxies. But it has a huge scatter at fixed mass. So you want ideally to have a proxy which is both cheap and low scatter, but that is hard to find. So just getting back to do some archaeology, which is I'm showing here the Planck sigma 8 controversy. So this is back from the paper by the Planck collaboration back in 2013. And what they've done is they've selected the clusters using the Synev-Zeldovich effect, and they compared the cluster constraints they were getting on Omegam and sigma 8 from cluster counts to what they were finding from CMB. And you see there was this discrepancy between the two. And this is better shown in this plot here, where you have here, this is just the number density of detected clusters. The red points are the number density of the detected clusters as a function of redshift. And the green curve is what you would expect to find if the CMB cosmology was perfect. And while what you would like to fit rather for the clusters is the blue curve here. So there is a discrepancy on the order of 2.5 times, so there should be 2.5 times more massive clusters in the local universe compared to what Planck has detected using the SZ effect. So quickly it was shown that there could be a way of reconciling those two measurements, which is to invoke the infamous mass bias. So of course what you want to do, as I told you, you're not detecting directly the mass of the system, you're detecting an observable, and you want to know how this observable is related to the mass. If you're making a systematic error when you do this, then you would shift the contours with respect to the true contours. And this is what is shown here with different types of, so this is encoded within this mass bias 1 minus b, which is the ratio of the so observed mass, meaning the mass that you expect you're finding, to the true mass. And if you think that this bias here was wrongly calibrated by the Planck team, then you may shift the contours in the direction of the CMB. So is that just one quick slide on what this 1 minus b actually means? Because for me, it's not just a parameter; it's also an important physical phenomenon. So the idea is that what the Planck team did is they used observations of these systems, of the gas of these systems, and then they assume hydrostatic equilibrium. So they assume that the gas in the system is in equilibrium within the potential well that is set by the dark matter. And then if you do that, then you have the pressure of the gas that you can measure, the density of the gas, and you can reconstruct the total mass. We've heard that already this morning. Then there is one big underlying assumption, which is that the gas in the system is fully thermalized, which may or may not be true. So if this is not true, then these masses estimated in this way are expected to be biased low on average. So the point I want to make here is that this is not just a quantity that you can shift up and down based on your preferred cosmology. It's actually a quantity that has an important physical meaning, so you can't just decide on your own, I don't like this value, so I want to preserve my cosmology. Okay, so here I'm just showing you an somewhat outdated, actually, collection of measurements, estimates of what this mass bias should be. The orange curve here is the orange point is what you should get in order to match cluster counts with CMB. And then you have a number of actual measurements of this mass bias in a different of ways. Here, these red points, they are direct wave cleansing comparisons. So what is done is you have measurements of the mass of systems from wave cleansing and from hydrostatic equilibrium, and you compare the two things. Then you have indirect wave cleansing comparisons. So in that case, you have measurements of the wave cleansing signal from these systems, and you have Planck inferred masses using the scaling relations that they assume for their analysis. Here, this is what you would get if you assume that you know the gas fraction of these systems, and you use this gas fraction as an anchor for what the true mass should be. And then finally, you can also just create mocks from hydrosims, so that's what we heard this morning, and estimate what this mass bias should be according to hydrosimulations. Generally speaking, the point is that there is a bit of scatter, but most of these methods converge toward the value of 0.8, which is higher than what you would need in order to reconcile CMB and cluster counts. Then, of course, in recent years, we have somewhat moved away from that. And what we are doing now is to use wave cleansing as our mass calibrator directly, because now we have wide area surveys, which we didn't have back 10 years ago. So what we are doing is we are directly measuring the wave cleansing signal from the clusters that we detect. Here is an example here for the XMM-XXL survey, which is pretty small, but still giving you a good idea of what can be done. And then this is just the stacked wave cleansing signal from all the clusters in that survey. The issue that we have here is that there is also a mass bias for wave cleansing, which primarily comes from the fact that we are assuming when we try to get the mass of a system, we are assuming that the mass distribution is an Navarro-Frank White, which may or may not be true. And in some cases, it's not true. That leads to some, like usual, underestimate of that lensing signal. And this actually may be mass dependent, as is shown in this recent paper by Giocoli et al. So what we are doing with more modern experiments, let's leave the 10 years ago world and move back to the more recent experiments. What we are doing now, we are using internal mass calibration, and we are forward modeling our observed distribution. So we start from a model for the mass function. We have a number of parameters which describe the scaling relation between the mass and our observable. We fold in our selection functions, and we have internal calibration of the mass of these systems through weak lensing. And then finally, we are fitting jointly with the number density of the detected clusters. I'm not going to go through all of this very scary slide, but just to give you an idea of what people are doing nowadays, they are starting from all those parameters, and they are building a giant forward model in order to fit at the same time for all of these constraints. And what we've already heard this morning, that the future is called simulation-based inference. I must say that I did not wait for this morning in order to use this slide and call it the future. So what we are proposing now in this paper that we are going to submit very soon by my student Manon is that we can generate simulations of a fiducial universe, fold in all our observational effects in order to create some mock samples, and then fit the simulated mock samples directly onto the constraints that we are finding. So here is what the sort of scheme that she put together. And what we've done in this paper is to see how this method can reconstruct the real clusters that we would find in a mock of extracted from n-body simulations. So we start from this light cone from n-body simulation, and then we extract a mock sample from the simulation in the same way as what we would do with the real data, and then we fit this SBI model. So here is what it looks like. So here in that case, we assume that we have histograms for the detected redshift distribution, flux distribution, temperature distribution of these clusters. These are all redshift independent quantities. And then we forward model all of that by generating lots of simulations and training a neural network to relate the input parameters to the generate mock dataset. And out of that, we can study a number of interesting effects. So for instance, we can see how our systematics on the mass calibration change. So here you have on the left-hand side fitting the same mock data, but changing the amplitude of this scaling relation between your mass and your observable. And you see that, interestingly, the constraints are changing along this axis here. And if you are at all familiar with the parameter S8 that we like to use for both cluster count and weak lensing cosmology, then you will see that it's actually staying along this degeneracy here, meaning that with this forward modeling approach, even if you get your mass calibration slightly wrong, then your S8 value is still going to remain roughly the same. What we looked at also is what happens if our constraints on the halo mass function is wrong. So of course we are relying on n-body simulations to tell us what the halo mass function is and how it's related to cosmological parameters. And here we are using several different halo mass function models and fitting the same mock data by changing this halo mass function. And you can see that even though these halo mass functions look quite a bit different from one another, then the constraints that you get in the end don't change much. So the associated systematics are subdominant. So back in 2019, this is the situation that we were in. we had this S8 tension with lots of measurements, preferring lower values of sigma 8 or S8 than what the CMB was telling us. But now we have many more and larger cluster cosmology experiments. I told you about eROSITA, SPT, and now we have Euclid and LSST, which are coming in and delivering lots of optical clusters. Just to briefly tell you what eROSITA is like. So it's a all-sky survey with wide field X-ray telescopes. Here is an image that this telescope has produced of the entire sky. And this is a zoom in on one of the region where here you have this massive cluster here, which is actually a double cluster with a bridge in between that was detected in the survey. And last year, the first cosmology results from eROSITA were presented. And here is where the omega matter sigma 8 contours lie compared to Planck. And roughly at the same time, at the end of last year, we had the latest SPT results coming in with more than 1,000 SE selected clusters. Similarly, here are the contours in red. And you see that there is no more tension between Planck and the most recent cluster cosmology experiments. So here, S8 tension no more. This is just taking the plot, the whisker plot from the white paper, where you see these green/yellow undefined color points compared to the CMB, which and all the most recent cluster experiments actually fall back on the Planck constraints. So then the last thing, of course, that we can do, if we think that now we have our systematics sorted out earlier than weak lensing, then we can try to now combine, of course, the data sets. And using that, we can try to get constraints on dark energy using the evolution of the halo mass function with time. And this is what was presented last year by the eROSITA consortium. And this is now the most recent SPT results. And interestingly, so you see what this SPT results show you the evolution of the sigma 8, measured sigma 8 parameters as function of redshift. So you can see that now we are also able to get to the evolution of this, which given the latest DESI results is going to be really interesting. So here is my conclusion. I think we have solved our main systematic, which was mass calibration. And we have done that by directly fitting weak lensing mass calibration within our joint cosmology framework. And when we do this, all the most recent cluster count experiments are no longer in tension with CMB. There is no longer a sigma 8 tension, at least for what concerns cluster count experiments. And of course, if that's the case, then it means we can go beyond and try to understand dark energy, and which I think is very timely, given the results we just heard from DESI. Thanks very much.
Thank you, Dominique, for a very interesting talk and very clear. Questions?
Okay, thank you for the presentation. I wanted to ask, regarding the results, especially in the comparison with Planck. Now, apart from the tension that you've seen for the contour plots sigma 8 omega m, what I noticed is that in many cases, the contours had different orientations. The contour, you see that they correlate for Planck, but they anti-correlate, for instance, for the Surnayev-Zerdonich effect. And I'm referring to the sigma 8 and omega m parameter. One, what would expect for those two parameters? They should correlate or anti-correlate?
For cluster counts, they anti-correlate. And that's due to the fact that, I mean, especially if you have a relatively narrow mass range that you're working with, then you can get more clusters or fewer clusters, both by just having more matter or having more clumpy matter. Okay. So you can get the same, if your constraint is cluster abundance, You can get the same cluster abundance by, on the one hand, increasing Omegam and decreasing sigma 8 or vice versa.
Okay, and for Planck instead, why do they correlate?
Oh, for Planck, okay, so for Planck I'm not completely sure, but it's not, okay, so I should think about this. But I mean, for Planck the correlation is somewhat lower than what you get for cluster counts. So I think I have this somewhere, yeah, here. Indeed, you have this mild correlation, but it's not huge. Of course, for Planck, it's a bit more involved because you have all this 6 parameter fit to lambda CDM, and
Okay.
yeah, it's. I don't have a clear feeling of why that is.
Okay, thanks.
I have a question regarding maybe your 6th or 7th slide where you are showing omega m0 and sigma 8 contour and 2016's results where SZ results are there and Planck results are there and there seems tension.
This one.
Yes. So do we have an update of this particular result, like using exactly SZ data and CMBTT and what happens in this particular contour space? Because I see many contours after this and different updated results, but not exactly using the same data. So what if we exactly use the same data and is there a tension or not?
I don't think this has been redone recently. I mean, I should say that the methodology that was adopted back then to get these cluster cosmology contours was very different from what we do today. That's what I wanted to show as well with this whole forward modeling approach with internal mass calibration. We didn't have any of that back then. So what was done was to assume an external scaling relation between mass and observable, and just try to get back to the cosmology in a more direct way. So by doing something like this, so actually constructing a halo mass function instead of forward modeling it. So things can go wrong in many different areas when you proceed in that way. So I'm not completely sure where they went wrong, but we can say in hindsight that at least in one place they went wrong.
Okay, so using the hello mass modeling, if we try to plot the same, there will be no tension at present. Do you think
I don't expect so. Yeah.
Let's thank the speaker.